So warm welcome to all of you in the lecture series of Basic Real Analysis. Uh, Today's lecture, we're going to continue with convergent sequences only. And this lecture starts with an errata. It starts with an errata. Uh, I think it's errata for your video number 2. That is Cauchy sequences 2, I guess. Okay. Okay, so the question there, I feel that I made a slight mistake. Kindly excuse me for that. The question said that xn plus 1 minus of xn mod, if it is less than equal to 1 or n squared, does it imply the uh, convergence of xn? And actually I made a slight mistake at the last step, so let us redo it again so that you do not get wrong things to understand. Okay, so let us try to prove it. So whenever it comes upon establishment of Cauchy sequences, one has to remember that you need to estimate, one needs to estimate what? One needs to estimate xm minus xn modulus for all m greater than n greater than equals to n not belongs to natural. This is what we need to estimate. So I'll let you know what was the error. And let's say this is your m, this is your m minus 1, this is your m minus 2, was your n, this was your n plus 1, and so on and so forth. If I need to estimate this and the information given to me is in terms of the difference between the two consecutive elements, what I need to do is I need to write it somehow in this fashion. Okay, and instead of xm, I would like to estimate xm plus 1 minus xn plus 1, because see uh, that I'll let you know why I'm doing this. It is one and the same thing. Instead of xn, I'm doing xn plus 1 minus xn plus 1. So basically here you'll add 1 1 1 and not. So basically I'm going to do this xm plus 1, and here I'm going to get minus xm, then I'll get plus xm minus of xm minus 1 plus xm minus 1 minus xm minus 2, and at the end of the day, at the end I'll get xn, uh, so instead of xn, so this is xn plus 1, this is xn plus 2, this would be xn plus 3. I'll get xn plus 3 minus of xn plus 2, and then I will get plus xn plus 2 minus of xn plus 1 modulus. So basically what is happening, I need to estimate xn plus 1 minus of xn plus 1, which indeed is equals to this, and by using the triangles inequality, what I'm getting this. Okay, so this is what you're going to have. Now you see, if this remains your case, that is xn plus 1 minus xn mod is less than equal to 1 upon n square. So instead of xm minus xn, I'm estimating xm plus 1 minus xn plus 1. The reasons you're going to get later on, because if I initiate from m, then see this will be xm minus xm minus 1, so this remains m minus 1 square, and somehow it creates I just don't like it. So basically what I've done, I've just added one term. So I'm estimating xm plus 1 minus xn plus 1. If I'm able to show it less than epsilon for all m greater than equals to n not belongs to natural, indeed I'm going to establish the Cauchiness of this particular sequence. I hope you're getting the point. And okay, so what I'm going to do is, let us say this would be equals to what? So this would be equals to, I should write less than equals to 1 over m square, then this would be 1 upon m minus 1 whole square, and then there would be, I think this would be m minus 2 whole square, and this would be plus 1 upon m minus 2 wholes, I think this would be right, m minus 3 whole square, and there would be some 1 upon n plus 2 whole square, and then there would be plus 1 upon n plus 1 whole square. I hope it is quite easy to see. Okay, now you see, in that particular question, what I made mistake was actually I replaced this, the mistake I'm writing it, mistake I'm writing, okay? In that particular question, I made a mistake. Everything was fine. So basically what I did was when I was replacing this entire thing by less than 1 upon n square, that is not a worry. That is absolutely fine. The problem was with the counting. So basically what I did, I forgot that m is more, n is less. So eventually I wrote it as n minus m. And that is a wrong thing to do because see, n is less than m is greater than n, so this particular validity does not hold. And what I did was, I think I divided by this and then I wrote like this, and this is certainly wrong here. Okay, so actually in the morning itself when I was teaching my students, I actually happened to go through entire process and actually I made a change for this particular thing. Please kindly note down this change so that you will not be able to make that certain mistake. Okay, so let us do that change. Okay, so what will happen? So what I insist here is that I should take a different approach. So I'm taking a different approach to tackle this situation. So what is the different approach I'm going to take? So this different approach that I'm going to tackle, I'm going to take in order to tackle this kind of thing is, let's say I'm dealing with m, okay, and I'm here dealing with n plus 1. So what is m? I know that m is greater than, sorry, m plus, or I should write m is greater than m minus 1, right? So I can simply write that my m square would be greater than m into m minus 1, right? And I can write that my 1 upon m square is less than 1 upon m into m minus 1. And this particular 1 upon m into m minus 1, I can write in this fashion. Okay. So most often these kind of mistakes may arise. I mean, I'm not defending myself, but I have made a mistake, so I'm just trying to bring an errata for you. And once you complete this, then we are going to do a little bit more of the questions today. Okay. So what I'm left up with is xm plus 1 minus xn plus 1 is equals to what? Is less than equals to 1 upon m minus 1 minus 1 upon m, right? Then you're going to have okay, I think this is absolutely fine, okay. This particular term, I know that my m minus 1 would be greater than m minus 2, and I can write my m minus 1 whole square greater than m minus 1 into m minus 2, and simply I can write 1 upon m minus 1 whole square is less than 1 upon uh, m minus of 1 and into m minus of 2. So what I will get, I'll get 1 upon m minus of 2 minus 1 upon m minus of 1. Then certainly it's quite easy to see that it will be 1 upon m minus 3, this would be 1 upon m minus 2, and additionally I'll let it go all along, and what it would be, so this is n plus 2 whole square, right? So this is n plus 2 whole square, so I should write in this fashion. See, this is your n plus 1, this is your n plus 2, right? This is your n plus 2, and there would be n plus 3 here, and so on and so forth. So what I'm doing till now, I'm actually comparing my term with a one lesser term. So n plus 2, if I compare it with, I'm writing it here somewhere. So if I compare my n plus 2 with n plus 1, what I will get, that n plus 2 whole square is greater than n plus 1 into n plus 2, right? So if I write it in this fashion, this will be 1 upon n plus 1, and here it will come as 1 upon n plus 2, right? And plus, and this whole modulus also. The last term would be, this is n plus 1. I have to compare it with n, so I'll get 1 upon n minus 1 upon n plus 1, right? So this is how you're going to get the terms. So instead of n plus 1 whole square, I'm comparing n plus 1 whole square with the, so for example, the last term, just pay attention to this term. What it would be? It would be n plus 1 whole square. So I'll write n plus 1 whole square. So instead, I'll write n plus 1 is greater than n, and I'll write that my n plus 1 whole square is greater than n square. And then, okay, so this is not working, right? N plus 1 whole square. Okay, this is something I need to see. Just give me a minute. So I'll see it back. Okay, till now everything is clear. I think this is quite clear to you. So this is what I'm absorbing right now. Okay, so this is something that I'm absorbing. the m terms are not making mistakes. So here is some mistake. Let us try to rectify this mistake. Okay, so what needs to be seen is, okay, so here you get xm minus xm minus 1, then xm instead of xm minus 1 I have taken xm plus 1, so xm plus 1 minus of xm, so I'm writing it here. This would be your xm plus 1. So here you will have xm plus 1 and here you have xm plus 1. Okay, uh, okay, so xm plus 1 minus xm, fine. Xm minus xm minus 1, fine. Xm minus 1 xm minus 2, fine. And here you have xn plus 3 minus of xn plus 2, fine. And then you have this xn plus 2 minus of xn plus 1, right? And what am I getting? If I abide by whatever has been said to me, it has been said to me that xn plus 1 n square. So this index is, you can, so if you see it there, this would be 1 upon n plus 2 whole square less than 1 upon n plus 1 whole square. This is absolutely fine till now. What approach I am taking? The approach that I am taking is similar to the telescopic series. I know that my m would be greater than m minus 1. So what I'm doing, I'm comparing it with one less term. Okay, I'm comparing it with one less term. Okay, and this is how it is going to be, right? So what I can do, I can write one more term here so that at least I get some insight. So just before, it would be 1 upon n plus 3 whole square. Okay, so if I want to compare this thing, and this thing is quite clear. If I have to compare m square, I'll write that my m is greater than m minus 1 and m square would be greater than m into m minus 1. And I can write that my 1 upon m square is less than 1 upon m into m minus 1. And certainly what I can do, I can write this particular stuff as m minus 1 minus 1 upon m. So here you can see, this is how it is. I hope it is clear. And certainly the different other terms I can write in this fashion. Now the problem is with n. So I'm just trying to construct a few more terms so that there does not remain any confusion. So what are those terms? So for example, this is 1, this is 2, this is 3. So what I can do is, I'm going for an order. You can see in the denominator, you have a decreasing thing. So there is m, then m minus 1, then m minus 2, then m minus 3, then m minus 4, so on and so forth. And then you have this n plus 3 whole square, n plus 2 whole square, n plus 1 whole square. So what would be n plus 3 whole square? What should I do? I think, what is my plan, that I would compare n plus 3 with n plus 2, right? If I compare n plus 3 by n plus 2, here I'll get n plus 3 whole square is greater than n plus 3 into n plus 2. And if I want to write 1 upon n plus 3 whole square, it would be less than 1 upon n plus 3 or 1 upon n plus 2. I'll write this way. So the third term before the penultimate term, I can write that it is less than, or strictly I should write, it's not even equal to, it's less than this, and just give me a minute. So this term would be then what? This term would be then what? I think this term would be, I should write this way, 1 upon n plus 2 minus 1 upon n plus 3, then plus, what would I get next? Next is what? Next is n plus 2. What is n plus 2? N plus 2 is greater than n plus 1. And I would write that my n plus 2 whole square is greater than n plus 1 into n plus 2. And here I can write it is less than 1 upon n plus 1 minus 1 upon n plus 1 whole square. So n plus 1 would certainly be greater than, n plus 1 would certainly be greater than n. And if I multiply n plus 1 both side, I'll get this. And certainly here I can write plus 1 upon n minus 1 upon n plus 1. Okay, certainly what you can see right now is modulus of xn plus 1 minus xn plus 1 being estimated as this. And just note the cutting pattern. Okay, whenever you are doing this, never try to go very fast in this, otherwise we'll make a certain mistake here. See, in any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. This is latter, so it will find a former here. This particular former part will find a latter here, but problem is with this 1 upon n cannot find a latter part. So that is why I actually took xm plus 1 minus xn plus 1. Else you would have had here 1 upon n minus 1, and that certainly I feel is I just feel that it is sort of out of symmetry. So I've taken this xm plus 1 minus xn. Had it been xm minus xn, then you would have got 1 upon m minus 1 here, 1 upon n minus 1 here. So certainly you can make a judgment from here that this particular thing, this particular thing is 1 upon n minus 1 upon m. And I clearly know that my m is greater than n, so certainly 1 upon m will be less than 1 upon n. So obviously this is positive. This is positive, and 1 upon n is being subtracted by something, so should I not write it as less than 1 upon n? And I know already that limit n tends to infinity, 1 upon n is equal to 0. That implies 1 upon n minus 0 can be made less than epsilon for all n greater than equals to n not belongs to natural. What does it implicate us? What does it tell us? It tells us that xn plus 1 minus of xn plus 1 can be made less than epsilon for all m greater than n greater than equals to n not belongs to natural, which implies that xn is a Cauchy sequence. So kindly get rid of the approach that I took in the lecture number 2 and kindly correct this particular thing, else right now it is fine, but overall it will lead to your difficult scenarios if you are going to continue with the same approach. So actually what I did there was, actually I tried to compare this particular series by less than 1 upon n plus 1 square. That is absolutely fine, you can do so, but actually the counting was wrong. I took it as n minus m, rather it is m minus n, and if I take m minus n, then things will not work the way we want. So kindly take this approach and kindly correct the lecture number 2 if you have made some notes out of it. Okay, so now let us move to some other questions and try to do more questions on Cauchy sequences. Let us try to do some more questions on Cauchy sequences only. Let us try to do more questions. Could be a Cauchy sequence or not. So question: which of the following are Cauchy sequences? Which of the following are Cauchy sequences? So, this is an, this is option number 1 I'm giving. An is equals to 1 upon 1 into 2 minus 1 upon, I think this is 2 in minus 2 into 1 upon 2 into 3 plus dash 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 minus 1 raised to power n minus 1 1 upon n into n plus 1. So kindly think about it and let me know whether this is a Cauchy sequence or not. Okay, so in order to judge for a Cauchy sequence, I have told you already what you need to do is you need to estimate modulus of am minus of an, and if at all you are able to prove it less than epsilon for all m greater than n greater than equals to some n not belongs to natural, you are done. One alternate definition to search for doing Cauchy sequences could be this. So you can also estimate x an plus k minus of an modulus. Okay, you can estimate this as well. So what this would be? So if you clearly see it around, so if I take this particular an plus k, here I'm writing an plus k. An plus k would be what? It would be 1 into 1 upon 1 into 2, 1 upon 2 into 3, 1 up, sorry, this is minus here, 1 upon 3 into 4 dash dash dash. Here you will reach till this point. You will reach this point because this is an, and then you are going to continue from here further. That is, you're going to write this plus minus 1 raised to power n, because you have instead of n minus 1 one more term, so n becomes n plus 1 here. So you'll get 1 minus 1 raised to power n, and here you will get n plus 1, and here you will get n plus 2. Instead of n plus 1, now you write n plus 2. So this will become n plus 1 here, and this will become 1 upon n plus 1, and here you will get n plus 2. And if you go on writing this, what you're going to get, the last term that you're going to get, see here it was n, here it was n minus 1. Okay, so instead of n, if I write n plus k, so last term would be minus 1 raised to power n plus k minus of 1 divided by 1 upon n plus k, and then you will have n plus k plus 1. I hope it is quite clear to you. Okay, now if you see, if I want to write an plus k minus an, what it would be equals to? it would be equals to modulus of, I'm writing it in a different pen, so it would be equals to modulus of minus 1 raised to power of n plus k minus 1 divided by n plus k, and then you will have this n plus k plus 1. Okay, then again the next term just before term would be what? It would be minus 1 raised to power n plus k minus of 2 divided by n plus k plus, sorry, this would be I think minus 1, and then you will have n plus k. Just a term before you will have n plus k minus 1, and this would be n plus k minus 1 plus 1, so this would be n plus k simply. Okay, and if I keep on doing this, it will be done till this point, because see, till this point an plus k, this is equals to what? This is an. So an plus k minus of an would be this term. Okay, so the last term that I feel would be minus 1 raised to power n divided by n plus 1 into n plus 2 modulus. So in totality, what I can write that my modulus of an plus k minus an mod is simply equals to modulus of minus 1 raised to power of n plus k minus 1 divided by n plus k into n plus k plus 1. Then again I will have minus 1 raised to power of n plus k minus 2 divided by n plus k minus 1, and then you will have this n plus k simply, and then you keep on moving. This would be minus 1 raised to power n divided by n plus 1 into n plus 2. Again use what is known as your triangles inequality, and then I can clearly write that my an plus k minus an mod will be less than equal to 1 upon n plus k into n plus k plus 1 plus 1 upon n plus k minus 1 into n plus k. Then you will have n plus k minus a 2, and then you will have n plus k minus 1 dash dash. What this would be, just a term before, it would be 1 upon n. Instead of n you just write n minus 1, so you'll get a before term, so you will get n into n plus 1, and then the last term would be 1 upon n plus 1 into n plus 2 modulus. Okay, so what you are going to get, let us write that. So eventually I know that I'm going to get what? Okay, I think this is quite clear. Have I made some mistake doing it? So just a term before, okay, till n plus 1 were there, right? Okay, so this was n and this was n plus 1. So last term would be, if I go till n plus k, so if I go till n plus k, so it will come out as n plus k. Here it would be n plus k plus 1, here it would be n plus k. Just a term before, it would be n plus k minus 1, and then it would be n plus k. So that is fine. And if I see here what it is, okay, so this is minus 1 raised to power n plus 1, and you have this n plus 2 here. The next term would be what? The next term would be, okay, what have I written? Okay, I have written the same thing, right? Okay, sorry. So this is n plus 1, this is n plus 1, this is n plus 2, this would be n plus 2, and this would be n plus 3, right? Okay, so if I see this particular term, what I will get, last term would be 1 upon n plus 1, 1 upon n plus 2, and this particular term would be not this, rather this would be 1 upon, it would be 1 this would be this term would be 1 upon n plus 2 into n plus 3, right? This would be this. Okay, now what you are going to get is simply modulus of an plus k minus an mod less than equals to, what I can write it as 1 upon n plus k minus 1 upon n plus k plus 1. Then you have this plus 1 upon n plus k minus 1 minus 1 upon n plus k, then plus 1 upon n plus k minus 2 minus 1 upon n plus k minus 1. Then add a few more terms in order to understand how is the cutting pattern, and then you're going to get 1 upon n plus 2 minus 1 upon n plus 3, and then the last term would be 1 upon, I think, n plus 1 minus 1 upon n plus 2. I guess till now everything is clear. Now you just see it, sorry, there is a modulus also, there is a modulus also. Now just try to see the cutting patterns. In any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. In any bracket, the former part is being cut by the next bracket's latter part. This is a latter part. It will find a former part here somewhere. So I'm left out with what? I'm left out with an plus k minus an modulus being less than 1 upon n plus 1 minus 1 upon n plus k plus 1. And clearly I know that this would be less than 1 upon n. Okay, and I know that 1 upon n can certainly be made less than epsilon for all n greater than equals to n naught belongs to natural. What does it imply? It implies that an plus k minus of an modulus can be made less than epsilon for all n greater than equals to n naught belongs to natural and k greater than 0. It implies what? It implies that my sequence an is a Cauchy sequence. I hope it is quite clear. If it's not clear, kindly let me know. Kindly let me know, whosoever is watching. If there is anybody watching, kindly let me know if certain thing you're not able to follow. Okay, I hope it is clear. Okay, now let us move a little bit further, and now I'm going to ask you yet another question, which is again from determining whether a sequence is Cauchy or not. So a few concepts you should remember. This epsilon del as such is not going to be asked in your examination. Okay, so you can skip this particular portion if you really feel that it is getting too much rigorous, but certain awareness of finding Cauchy sequences or writing proofs for Cauchy sequences by epsilon approach can indeed be very fruitful for your interviews and also very fruitful for your overall development of mathematics. Okay, so there can be two approaches to learn mathematics. One can be applicative approach, another one can be proof writing approach. Obviously, when it comes to competitive examination, you need to focus more on applicative side, but you should not forget that eventually that the proof writing skills should remain inherent to your way of working. Even if you're not doing it, try to read the proofs and all those things so that you remain quite close to your proof writing approaches also. Otherwise, even if you get selected to some institutions, there you're going to face difficulties. Okay, so this is a kind of thought I had given to you. What do you think about this particular sequence, that is an given by alpha 1 raised to power q1, q raised to power 1, alpha raised to power q square, alpha raised to power 3q cube, and dash 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 alpha raised to power n, q raised to power n for modulus of q less than 1, and alpha k is such that it is bounded for all k is equals to 1, 2, 3, and so on and so forth. Okay, so this is what has been given in the question, that your alphas which are governed by alpha 1, alpha 2, alpha 3 till alpha n, they are bounded, and q1, q2, q3 till q raised to power n, where q mod is less than 1. Now you need to tell me, what is this sequence? Is it a Cauchy sequence or not a Cauchy sequence? So we need to see whether this is a Cauchy sequence or not a Cauchy sequence. And again, the same approach I will follow, and I'll follow it quite quickly so that I jump onto now monotone convergence soon. And what would be proof for it? I'll prove it. In order to prove that this is a Cauchy sequence, all I need to see is an estimate of an plus k minus an. Okay, now if I do so, what I would get? I would get something like this. I would get something like this, alpha n plus k, and I will get q raised to power n plus k, then I will get alpha, this is equals to this would be alpha n plus k minus 1, and this would be n plus k minus 1, and then dash 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 last power would be alpha n plus 1 q raised to power n plus 1 modulus. and I know I can make it less than equal to some m, because all of these can be written less than m, and then I can write qn plus 1 modulus, then I can write qn plus k minus 1 modulus, and dash 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 q, and modulus, sorry, qn plus 1 modulus. Now whether I take a modulus and then take a power, or I take a power and then take a modulus, this is one and the same thing. So I will write that my alpha n plus k, sorry, a n plus k minus a n modulus is less than equal to m times q modulus of n plus 1 plus q modulus of n plus k minus 1 and dash 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 q modulus of n plus 1 here. Now if you see slightly, there is a mistake. I think this is n plus 1, this is n plus k, sorry, this is n plus k, this is n plus k, okay, this is n plus k, right? So this is n plus k, then you will have n plus k minus 1, at the end you will have q raised to power n plus 1. If you think slightly about this, what is this? You know that your q modulus q modulus has been given to you to be less than 1, right? So it implies that this particular thing, if I write in if you see, if I am writing it in this fashion, okay, so I'll write it in this fashion so that you are able to get it. Okay, so I'll write again, a n plus k minus a n mod is less than equal to m times modulus of q raised to power n plus 1. Then we'll get q raised to power n plus 2 and dash 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 mod q raised to power n plus k minus 1, and the last term you will have modulus of q raised to power n plus k. Okay, now this is particularly a geometric series, and I know that the geometric series is convergent if modulus of q is less than 1. So I can write this as m modulus of q raised to power n plus 1, then 1 minus modulus of q happens to be the common ratio, and how many number of terms are here? N plus k minus n plus 1 plus 1. So always remember, when you have to calculate the number of terms, if you're decreasing, if you're subtracting from this minus this, don't forget to add 1, otherwise you'll get a mistake here. So you'll get what? You'll simply get here modulus of q raised to power k divided by 1 minus of modulus of q. And certainly this particular thing I can write it here, that modulus of a n plus k minus a n would be less than equals to m times 1 minus q division, and then I get q modulus raised to power n plus 1. And now if n tends to infinity and q modulus is less than 1, and here you have raised to power n plus 1, this goes towards 0. What does it imply? It implies that this particular thing can be made less than epsilon for all n greater than equal to some suitable number, let's say n naught, and here k is greater than 0. Certainly this implies that my sequence an is a Cauchy sequence. It certainly implies that my sequence an is a Cauchy sequence. Okay, so this is clearly a Cauchy sequence. Okay, now today I'm going to start with something called as Cauchy criterion of monotone criterion of convergence of sequences. So that is an important aspect for your question solving skill as well, and this is an important theorem. Cauchy sequences we have done to a great extent. Now let us start this. Let us start with monotone sequences. Let us start with monotone sequences, and we say that a sequence is if it is either increasing or decreasing. If a sequence is either increasing or decreasing, then we say that our sequence is a monotone sequence. So for a sequence to be monotone, it should be either increasing or either decreasing. If I'm saying that sequence is increasing, that implies that xn should be less than xn plus 1 for all n belongs to natural. And if I'm saying that my sequence is decreasing, that xn must be greater than xn plus 1 for all n belongs to. Now you see how to establish the convergence, how to establish a convergence. So here let xn be an increasing sequence. Let us say that xn be an increasing sequence. Let xn be an increasing sequence. Then it would be convergent if it is bounded above. If and only if it is bounded above. And if I say the same, let xn be a decreasing sequence, then it would be convergent if and only if it is bounded below. Then it would be convergent if and only if it is bounded below. Okay, so this is something that you should remember. I'm not deriving it, but understand this is an important property, that if your sequence is bound, if is an increasing sequence, then it would be convergent. Okay, it would be convergent if and only if it is bounded above. If it is like increasing, then one has to somehow confirm that it is bound. If somehow confirms that it is bounded above, then it would be convergent. And let xn be a decreasing sequence, then it would be convergent if and only if it is bounded below. What should I say? This is an important, you can say, sort of two theorems. These two theorems are very important when it comes to establishing the convergence of sequences. When it comes to about establishing the convergence of sequences. Okay, so in this regard, let us do a few questions, and then we'll do some other things as well, because till now I have not told you how to find limits of a sequence. So one has to be good at that particular thing. So let us do the first question. Let us do the first question in this particular series. The question says that, okay, next question. Okay, so question says that, just give me a minute. The question says that, the question is, let an be a bounded sequence. Let an be a bounded sequence, and it is given that an plus 1 is greater than equals to an minus 2 raised to power minus of n. An plus 1 is given to be greater than equals to an minus 2 raised to power minus n. We need to show that an is a convergent sequence. We need to show that an is convergent. We need to show that an is a convergent sequence. So this is the first question that I'm taking right now. What does it suggest? It suggests us that an plus 1 is greater than equals to an minus 2 raised to power minus n, and we need to assert that whether or not, how would our an behave, that is whether an would be convergent or an would not be a convergent sequence. This is what you need to prove. So I'm giving you a minute or so. If you're not able to conclude, then I will conclude it for you. Okay, so how to go about it? So see, whenever it comes to dealing with sequences and proving it monotone and all those kind of thing, one needs to see that how is your xn plus 1 minus xn behaving. Okay, so one needs to see the sign of, but usually what it would be like, so usually you would be supplied with some question here, xn, and what you do, you just replace xn by xn plus 1, and then try to take a subtraction. You see whether it is positive, negative, and then you try to assert about increasing or decreasing. Obviously, at times you need to take a little bit of hint by placing some values of n. So for example, you place n equals to 1, n equals to 2, n equals to 3, so on and so forth. Okay, but understand the point that it is not always feasible. Let's say this is one question where the feasibility is could not be seen. See, here you have an inequality rather than equality. You have an inequality. So I'll show some of the questions in this form also, but I've taken the bigger question or difficult question at very first, so that you actually tend to actually I want you to actually come to the point directly. So this is a difficult one, especially for the people who are doing it for the very first time. It would be a difficult thing to say. You have some structure, xn plus 1 is given to be, let's say, equals to 1 plus xn, or let's say 2 plus xn divided by 1 plus xn. Now here life is certainly easy. You just need to subtract xn, here subtract xn, try to make some assertion regarding this, and then try to show that whether it is bounded up, bounded below, or bounded above. This is something that you do usually. But in this question, this particular approach cannot be applied. Why it cannot be applied? Because here you have inequalities applied to you. So what I would do, I would actually define my new sequence. So this would be an approach. So let Bn be defined as, see, here this 2 raised to power minus n is here, and here you have n plus 1. So what one needs to see, that if at all I would be replacing my n by n plus 1, this particular thing should remain n. So what I would do, I would write Bn as simply an minus 2 raised to power 1 minus n. And why I'm doing it so? Because if I replace my Bn by Bn plus 1, this would be n plus 1, and here you will get 2 raised to power uh, minus of n. So this is why I'm doing it. So what would be your Bn plus 1? Your Bn plus 1 would be then given by an plus 1 minus 2 raised to power minus of n. So this is your equation number 1, and this is something I can write as equation number 2. Now if I try to conclude about, if I don't know about an, fine, that is absolutely fine. Even if you don't know about an, fine. All you know about an is that your an is a bounded sequence. You know that your an is a bounded sequence. Apart from this, you do not know anything. Apart from this, you do not know anything. So your an is a bounded sequence, and let us say I want to calculate my Bn plus 1 minus of Bn. What would be my Bn plus 1 minus of Bn? It would be simply an plus 1 minus of an, and then you have minus 2 raised to power minus of n, and then plus 2 raised to power 1 minus of n. I hope it is clear. So eventually I can write that Bn plus 1 minus of Bn would be equals to an plus 1 minus of an, and minus what? I take a 2 common out, 2 raised to power minus 1 minus n common out, I'll get 1 here, and then I will get what? This is simply, I think, if I take, so it will be this. Okay. I have taken 2 raised to power minus n common now. Okay, so if I take 2 raised to power minus n common, have I made a mistake or somewhere? I don't know. I think this is quite clear, right? Should I see it all over again? So if I do one thing, uh, if I take minus 2 raised to power minus n common out, I'll get 1, and here I will get minus of 2, right? So if minus of 2 and minus of 2, so I'll get have I made a mistake somewhere? I don't know. What I'm doing, I'm subtracting it. Okay, so if I'm subtracting it, 2 raised to power minus and minus minus, this would be plus. And if I take 2 raised to power minus n common out, so if I take 2 raised to power minus n common out, I will get 1 here, and I will get minus 2. Okay, this is what I'm getting. So eventually I know that my Bn plus 1, I think there was minus there, right? Just give me a minute. I think I have made a mistake somewhere. The question is fine. Question is fine. An plus 1 is greater than equal to an minus 2 raised to power minus n is there. And if I'm subtracting it, I'm getting an plus 1 minus of an, because an, this is fine. I think this is fine. If I replace it by n plus 1 here, so I'll get n plus 1 If I replace it by n plus 1, right? So if I replace it by n plus 1, I will get this only. Fine, this is absolutely fine. I don't think there is a mistake till now. If there is a mistake, kindly let me know. I think this is quite clear. I'll do it somehow, but just think about it. If I made a mistake, kindly let me know. And then we'll do a few more questions, okay? Okay, I think this should be right. I think this should be right. So what I'm getting is minus bn, bn plus 1 minus bn should be equals to an plus 1 minus of an, and then I think I should get 2 raised to power minus n. Okay, fine. Whatever is coming. Let us see. So this is what I'm getting right now. Okay, this is what I'm getting right now. Now what has been supplied to me? It has been supplied to me that an plus 1, I'm writing it here. So an plus 1 is given to be greater than equals to an minus 2 raised to power minus of n. Okay, and if I write it in this fashion, that an plus 1 minus an plus 2 raised to power minus n would be then what? It would be greater than 0. It is given to be this only. So if an plus 1 is given greater than equals to an minus 2 raised to power minus n, what does it imply? It implies that an plus 1 minus of an plus 2 raised to power of minus of n would be greater than equal to 0. And what does it imply? It implies that your bn plus 1 would be greater than equals to bn, right? Because bn plus 1 minus bn is nothing but this is the thing. Okay, what does it imply? What does it imply? Think about this. If bn plus 1 is greater than equal to bn, does it not imply that your bn is an increasing sequence, right? So it implies that my bn is an increasing sequence. Now, what has been given to you? It has been is a bounded sequence. So I can write that my bn, which is given by an minus 1 upon 2 ki power, I think this was 1 minus n. Now think about this. What can you think about this? So this will be, I think, 2 raised to power n minus 1, right? 2 raised to power 1 minus n. If I write 2 raised to power 1 minus as 1 upon 2 raised to power n minus 1, I don't think it should trouble you at all. And I know already that as n tends to infinity, 1 upon 2 raised to power n minus 1 tends to 0. It implies that this particular sequence is convergent. And every convergent sequence is a bounded sequence. And since bn is increasing, it implies bn is monotone. And if I'm saying that my sequence is monotonically increasing and plus bounded, it implies that bn is a convergent sequence. I hope it is clear. If anybody has got any problem, please you are free to ask me any sort of doubt right now. If there is any doubt, kindly let me know, and then we'll move to another question. Okay, I hope it is clear. Now just think about this question. Just think about this question. Okay, just think about this question which I'm giving it to you right now. Okay, and this is again an easy question. It's not that difficult, but at times I've found that people not giving simple answers. I mean, at times it may so happen that you are doing a simple question and you're not able to figure out, and at times you may crack a difficult one. So this is an easy question. Just give me a minute and I'll write it for you. So for example, I'm given a sequence. I'm writing given a sequence of let's say this is an, given a sequence an of given a sequence of positive integers, define what Sn is equals to 1 upon a1 plus 1 upon a2 dash 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 1 upon an. And another sequence that I'm defining is sigma n is equals to 1 upon 1 plus a1 into 1 upon 1 plus a2 dash 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 1 plus 1 upon an. Sorry, 1 plus 1 upon a1, 1 plus 1 upon a2, 1 plus 1 upon a. Now I'm saying if converges, then it implies ln sigma n converges. This is something that we need to see. Then we need to see that ln sigma n converges. Always remember, whenever we have product, I'm so sorry, and if I apply log to it, then log of a into b into c into d is log of a plus log of b plus log of c plus log of d. Now see what has been given to us. It has been given to us that Sn is a Cauchy sequence. So what has been given to us is that Sn is a Cauchy sequence. If Sn is a Cauchy sequence, what does it imply? I'm writing it here. Since Sn is Cauchy, so I can write Sn plus k minus Sn modulus can be written less than epsilon for all n greater than equals to n naught and k greater than 0. Right? So this is your Sn. This is how your Sn behaves. This is how your Sn behaves. Now you see uh, what has been given to you. I think we need to find about ln sigma n, right? So what would be your ln sigma n? So I'm writing ln sigma n would be simply log of 1 plus 1 upon a1 plus log of 1 plus 1 upon a2 dash 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 log of 1 plus 1 upon an, right? And what would be ln sigma n plus k? So it will be equals to till this, it will be there, and then there would be log of 1 plus 1 upon n plus 1, then plus log of 1 plus 1 upon an plus 2, and then dash 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 ln 1 plus 1 up log of ln of 1 plus 1 upon n plus k. Okay, and till this, if I subtract this, what will I get? I will get simply what will I get? I will simply get ln of sigma n plus k minus ln of sigma n, equivalent to writing ln of 1 plus 1 upon an plus 1. Okay, this is I think quite clear to see. Okay, okay, and then you'll get plus ln of 1 plus 1 upon an plus 2, and then you will have dash 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 ln of 1 plus 1 upon an plus k. And don't forget what has been given to you. It has been given to you that your Sn, which is this, is convergent. If it is convergent, it implies this is a Cauchy sequence. Okay, it implies this is a Cauchy sequence. Okay, so I hope I am audible. I think okay, so I think I'm audible. Okay. Okay, so sorry for the interruption because actually somehow the network went. So okay, so eventually now till now it is quite clear, and I'm already stating that Sn plus k minus Sn modulus is less than epsilon. Okay, sorry for the network interruption all over again. Actually, there was a network cut. So okay, Fine. So this question is giving us hard time, right? So okay, no issues. So the question was actually what I was stating was that Sn plus k minus Sn modulus is less than epsilon, right? So if it is this the case, then what I can write? I can write that my 1 upon An plus k plus 1 upon An plus k minus 1. Okay. I hope the network has resumed. So this question again, as I told you, is giving me hard time because of network. Okay, no issues. So the question was, just give me a minute. The question was plus k plus 1 upon n plus. Okay, I think it is now clear. Okay, now I hope it is clear, and I think now it is not going to give me hard time. See, what was question? Question discussed was being discussed as this. So Sn plus k minus of Sn modulus less than epsilon, it implies 1 upon n an plus k, 1 upon an plus k minus 1 dash 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 1 upon an plus 1 can be written less than epsilon. Okay, this can be written less than epsilon for all n greater than equals to n naught belongs to natural and k greater than 0. Now, what has been asked to you? It has been asked to you, what can you say about ln sigma n? What can be said about ln sigma n? And actually, I did it this way. Actually, I subtracted ln sigma n plus k minus ln sigma n, and I got this. Now, how to relate both of these things? See, what has been given to you? It has been given to you 1 upon an plus k plus 1 upon an plus k minus 1 dash 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 1 upon an plus 1 is less than sigma. So what I will do, I would use an identity from calculus. I will use a, sorry, identity, I'll use a, what you can say, I'll use something from calculus. And I know that ln of 1 plus x is always less than x. How come? Take your function fx for all x greater than 0 and define it as log of 1 upon, sorry, log of 1 plus x minus x, and now try to differentiate it. If you differentiate it, what you will get? You will get 1 upon 1 plus x minus 1, which is certainly minus x minus 1 plus 1 divided by 1 plus x, and certainly it will be less than 0. Why less than 0? Because x is greater than 0. If x is greater than 0, this particular thing would be less than 0 because minus x is here and 1 plus x is here. It implies f, it implies that f dash x is less than 0. It implies what? It implies fx is a decreasing function. And if fx is a decreasing function, for all x greater than 0, I can write that fx would be less than f0, right? Because fx is a decreasing function, so I can write fx would be less than f0. And what is f0? You write 0 here, log 1 is 0, and 0 here. 1 is x is 0. So you'll get log of 1 plus x is always less than x. So now if you just see what is ln sigma n plus k minus ln sigma k is ln sigma n, it would be equals to ln of 1 plus 1 upon an plus 1. Certainly it is less than x, so here this is x, so I'll get less than an plus 1, then I'll get an plus 2 and dash dash dash, at the last I will get an plus k, and this I will get 1 upon an plus k, sorry, the last term would be n plus k minus 1, that's just 1 upon an plus k, 1 upon k minus 1, here you will get I think n plus 2 only. Okay, I already know that this particular quantity is less than epsilon. Why it is less than epsilon? Since I know that my Sn converges. Since my Sn converges, then 1 upon an plus 1 1 upon an plus 2 dash 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 1 upon an plus k minus 1 and 1 upon an plus k 1 upon an plus k. All these things can be written less than epsilon. What does it imply? It implies that ln sigma n plus k minus ln sigma n can be made less than epsilon for all n greater than equals to n naught belongs to natural. We take a mod also, that for 2. Okay, I hope it is clear. So this is what we wanted to find, right? This is what we wanted to find, right? So I'll take a mod here as well. So mod, and this would be like this, and everything else would follow. And since okay, it has already been given that it is for positive integers only, so 1 upon a1 and all those things are positive. Even if you don't take a mod, it is 1 in the same thing. Okay, and ln 1 plus something is always positive, so ln 1 is 0 and ln 1 plus something is always positive. So even if I have had forgotten the mod, obviously from here you can do this thing. You can write it in this fashion. You can write in the triangles inequality, and then the things would follow. Okay, so I hope this is quite clear to you. Now try to do one question and then we'll meet tomorrow. Try to do this question. Suppose that Pn is equals to, it is given by 1 plus 1 upon 3 into 1 plus 1 upon 9 dash 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 1 plus 1 upon 3 raised to power n. Okay, then we need to prove that the sequence Pn converges. We need to prove that sequence Pn converges. How to prove it? Just think about it. I've done something in a previous lecture, a previous question, and then you will be able to see. See, I already know that 1 plus 1 upon 3 raised to power n would be greater than 0 for all n belongs to natural. That it would be positive. It would be positive. Okay, and it is quite easy to see that Pn is an increasing sequence. Why it is an increasing sequence? If you just think, what would be Pn plus 1? So Pn plus 1 would be what? Pn plus 1 would be 1 plus 3. I'll first write what would be Pn. Pn would be 1 plus 3 into 1 plus 9 dash 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 1 plus 1 upon 3 raised to power n. And what would be Pn plus 1? So if I write Pn plus 1, it would be simply 1 plus 3. Here it will be 1 plus 1 upon 9. And here it will be 1 plus 1 upon 3 raised to power n. And then you will have 1 plus 1 upon 3 raised to power n plus 1. And if I take log on both sides, what I will get? I can simply write that my ln of Pn plus 1 would be simply ln of Pn plus ln of 1 plus 1 upon 3 raised to power n plus 1. That is simply, and if I want to write, see, if I take a log here, so log of a into b into c into d is log of a plus log of b plus log of c plus log of d. So if you can see that log of Pn plus 1 minus ln of Pn would be what? It would be greater than 0. Why greater than 0? Because log of 1 plus x, so it is like log of 1 plus x. Anything if you raise, like for example, I know that my log 1 is what? My log 1 is simply 0. What would be log 1 plus x? It would be greater than 0 anyway. So it would be greater than 0. It implies log of Pn plus 1 would be greater than ln of Pn. And you see log is an increasing plot. Log is an increasing graph. So it implies that your Pn plus 1 should be greater than Pn. Also that it is 1 1. So your sequence is increasing. So your Pn as a sequence is increasing. Pn as a sequence is increasing. Okay, so I'll write it here that my sequence Pn is increasing. Now if my sequence Pn is increasing, all I need to prove that it is bounded. So what I'll do, I'll again take the help of log. So log Pn would be equals to what? It would be 1 upon 1 plus 3 here, plus log of 1 plus 1 upon 3 square here, and dash 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 log of 1 plus 1 upon 3 raised to power n here. And I have just stated that log of 1 plus x is always less than x for all x greater than 0. Okay, so I can write that my log of Pn would be less than 1 upon 3 plus 1 upon 3 square dash 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 1 upon 3 raised to power n minus 1, and lastly 1 upon 3 raised to power n. Okay, what does it imply? this is a geometric series, this is geometric series, and it is quite easy to see that it will be 1 upon 3, 1 minus 1 upon 3 raised to power n minus 1 upon 1 minus of 1 by 3. Certainly it is less than, I think, 3 by 2, because this will be 2 by 3, right? I think it would be 2 by 3 here. If it is 2 by 3 here, okay, so I'll write it here. So it is 1 by 3, 1 by 3 square, dash 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 1 upon 3 n minus 1, and last one will be 1 upon 3 raised to power n, right? So it would be less than in any case, because if you just think about this, I think this would be less than, I should write what? Even if I take n tends to, see, it would be less than 1 upon 3 divided by, so even if you take this term, so it is getting subtracted by something. So if I just take that it is less than this encircled this particular quantity, it would be 1 upon 3 minus 1 upon 3. I think it would be less than 1 upon 2. It would be less than 1 upon 2. So in any case, I can say that this would be bounded. If ln Pn is bounded, is less than, let's say, 1 over 2, I can say that my Pn is less than e ki power 1 upon 2. E ki power 1 upon 2. It implies that Pn is bounded. And if Pn is bounded, then it implies that Pn is increasing, that is monotone, plus bounded. So if a sequence is monotone as well as bounded, then it is convergent. If a sequence is monotone plus bounded, then it is convergent. Always remember that. I hope it is quite easy to see, and I'll hope to meet you tomorrow with further questions. I think there were some technical glitches today, so kindly excuse me for that. But overall, I hope that this particular session is fruitful for your preparation. Kindly join us live at 10:30 or probably at 10 p.m. In this particular time daily. We're going to dedicate 1 hour to our real analysis and ordinary differential equation preparation for your various competitive examinations like TIFR, NET, GATE, and JAM. I wish you all the best for your future. Till then, take